Hey everyone, and welcome to this explainer. Have you ever caught yourself wondering what actually makes an app smart? You know, how it seems to know exactly what you want? Well, today we are literally dissecting the brain of a computer program. We're going to look at how a program adapts to real-world inputs instead of just mindlessly following a rigid, fixed list of instructions. We are talking about the logic of selection structures. Okay, let's dive into this. Imagine you can't answer a simple question like, what happens if a score is greater than or equal to 50? Without a way to answer that, a program is essentially just a dumb linear script. It'll just spit out the exact same output every single time, no matter what's going on around it. Selection structures are the magic that allows a program to look at a piece of data, like, say, a test score, and actually make a dynamic, on-the-fly decision. So, here's our roadmap for today. We'll start by exploring the power of choice, and then we'll meet the specific selection structures. After that, we'll compare how Python and Java handle this, look at relational and Boolean operators, trace some program flow, and finally, go over how to avoid common coding mistakes. All right, part 1, the power of choice, making programs smart. So, the crucial point is that adding selection to our code makes it adaptable. It's the very foundation of how programs adjust to things like user input and validation rules. Think of a selection structure kind of like a strict bouncer at a club, right? It looks at a condition, maybe something like, is this user over 18, or is the password correct? And it evaluates it strictly as true or false. Based on that single true or false result, it decides which path of code gets the VIP treatment and gets to run. This is exactly, and I mean literally, how your favorite apps adapt to changing real-world scenarios. Moving on to Section 2, meet the selection structures. These are our tools for branching paths. You can think of these structures as the ultimate toolkit for creating branching code paths. And the absolute most basic tool in our kit, that's the simple if statement. You use this one when there is really only one specific action you want to test for. For example, if a user clicks a button, run this code. If the condition is true, boom, the block of code runs. But if it's false, the program just totally ignores it and goes right on its merry way. Next up on the list, we have the if-else structure. You're going to use this when you have exactly two possible outcomes. It absolutely guarantees that one, and actually only one, of two mutually exclusive paths will run. Think about checking a student's grade. If the score is 50 or above, the program prints pass. Else, it prints retry. There's no middle ground here, you know? It's always going to be one or the other. Finally, we get to the if, elif, else structure. You reach for this when you have a whole bunch of mutually exclusive outcomes to check. The program is going to evaluate these conditions right in order. And here is a super crucial rule to remember. Once a match is found somewhere in this chain, the program runs that block and completely ignores the rest. It literally doesn't even look at them. Let's move to Section 3 and see how this builds into real code. Python versus Java. Two dialects, one logic. Okay, so when we look at Python, you'll notice it relies heavily on formatting. It uses a colon right after the condition and relies on strict indentation, literally the blank space on the left side of the screen, to show which statements belong to which block. It also uses that handy shorthand, elif. Now, Java, on the other hand, is a bit more explicit with its punctuation. It uses parentheses around the conditions, curly brackets to clearly mark the beginning and end of code blocks, semicolons to end statements, and it spells out else if as two separate words. But here's the thing. Regardless of whether you use indentation or curly brackets, the underlying logical idea is exactly the same. Test a condition, choose a branch, and then keep going.
All right, Section 4, relational and Boolean operators, the gatekeepers.
Now, what's really interesting about this slide is seeing the strict rules that actually act as the gatekeepers to our branching paths. You probably recognize most of these relational operators from middle school math class, right? Less than, greater than, less than or equal to, but pay special attention to the bottom two. A double equal sign strictly checks if two things are exactly equal to each other. And an exclamation mark paired with an equal sign, that means not equal to. These operators are the absolute core of our true or false evaluations. And honestly, confusing them is where so many bugs are born.
But wait, what if we need to check more than one thing at the exact same time? Well, that is where Boolean operators come to the rescue. We can combine our relational operators with and, or, and not to get incredibly precise control. For example, let's say we want to figure out discount eligibility at a store. We might write a condition checking if a customer's age is greater than or equal to 65, or if their member status is true. Because we used or, only one of those conditions has to be true for the code to give them the discount.
Now, if we used and instead, they'd literally have to be a senior citizen and a member to get that lower price.
Moving into Section 5, Tracing Program Flow. We are going to start thinking like a computer. And this brilliantly illustrates how we actually walk through a piece of code exactly the way a computer reads it. Let's trace it step by step. In Step 1, our program sets the starting scene. The temperature is 12 and the condition wet is true. In Step 2, the computer hits its very first if statement. It asks itself, is the temperature less than 0? Well, 12 is definitely not less than 0, so that evaluates to false. The computer just entirely skips that block of code. Then, in Step 3, it moves to the next branch, an elif statement, and checks, is the temperature less than 15 and is wet equal to true? Let's see, 12 is less than 15 and wet is indeed true. Because we used an and operator, both parts are true, so the entire condition evaluates to true. The program confidently enters that block and outputs cold and wet.
And finally, Section 6, Avoiding Common Mistakes, Pitfalls to Watch Out For. I want to frame these not as failures, but just as totally typical hurdles that all developers face when writing flexible code. Let's rapid fire through them. First up, using a single equal sign instead of a double equal sign. A single equals attempts to assign a value, whereas a double equals checks for equality. Next, forgetting your indentation in Python or your curly brackets in Java. That's a classic. It'll cause frustrating syntax errors or worse, make the wrong statements run. Then, there's writing impossible logic, like checking if a mark is greater than 80 and less than 50. I mean, no way. That can literally never be true. But perhaps the most insidious mistake is putting your conditions in the wrong order. More specific cases often need to appear before broader ones. If a broad condition is placed first, it's going to trigger as true right away. And because we know the computer skips the remaining branches, your later more specific branches might never run at all. This will cause incorrect output even if your syntax is 100% perfect.
So, I want to leave you with this final provocative thought to ponder the next time you're building a smart program. Are your conditions in the right order? It sounds simple, but always double-check your code paths. Be mindful of your specific versus broad conditions, and honestly, you'll be writing flawless, highly adaptable selection structures in absolutely no time. Thanks so much for joining me for this explainer, and keep coding.